In the early 1900s, in the forests of the Pacific Northwest, a logging crew faced a problem no team of horses could solve. A giant fir had been cut on a steep mountainside. The trunk was longer than a city street, weighed many tons, and lay beyond any road or railroad. Then, somewhere uphill, an iron machine began to hiss. Steam filled its cylinders. A steel drum started turning. Steel cable tightened through the trees until the forest rang like an instrument. Slowly, the log moved. It tore through mud, crushed brush, jumped over roots, and slid toward the machine with enough force to shake the ground beneath the crew's boots. The machine was called a steam donkey. It did not look fast. It did not move under its own power. It often sat in one place for days. But from that position, it could drag enormous logs out of terrain once considered impossible to harvest. So how did this strange machine conquer America's steepest forests and help feed the lumber industry that built modern cities, railroads, mines, and entire regions? Before steam power entered the woods, nearly every log moved by muscle. A crew could cut a tree with axes and crosscut saws, trim its branches, and roll the trunk into position. But once that tree was on the ground, the real problem began. Timber was only valuable if it could reach a river, a railroad, or a sawmill. And in many American forests, that journey was far harder than cutting the tree itself. Horses and oxen pulled logs along rough skid roads built from smaller timbers laid across the ground. In winter, snow and ice reduced friction and made hauling easier. In dry weather, workers sometimes poured water over the road to create a frozen surface. But mud, rocks, deep ravines, and steep slopes could stop an entire operation. A single large log might weigh several tons. If it wedged between two stumps, slid sideways on a slope, or sank into soft ground, the animals could exhaust themselves without moving it more than a few feet. Worse, the team had to stand close to the load. A rolling trunk, broken chain, or panicked horse could injure men and animals in seconds. This meant logging companies were forced to ignore valuable trees simply because they stood too far from water or too high on a mountain. The forests were full of lumber, but much of it was commercially unreachable. America did not need stronger horses. It needed a machine that could stand still, pull from a distance, and keep working long after muscle had reached its limit. By the middle of the 19th century, America's appetite for timber was growing faster than its easiest forests could supply it. Cities needed lumber for houses, warehouses, docks, and factories. Railroads consumed enormous quantities of wood for ties, bridges, trestles, stations, and fuel. Mines required heavy timbers to support tunnels underground. New farms, mills, and settlements demanded barns, fences, wagons, and buildings. Every mile of expansion required more trees. At first, logging companies worked close to rivers and on relatively gentle ground. Winter snow turned rough trails into natural sled roads, and logs could be floated downstream when spring floods arrived. But the most accessible stands were cut first. Year after year, crews were forced deeper into the continent and farther up the mountains. In the Pacific Northwest, they encountered forests unlike anything eastern loggers had known. Douglas fir, western red cedar, and Sitka spruce could rise more than 200 feet. Their trunks were so wide that several men could stand across a single stump. Once felled, these trees became massive cylinders of dead weight, lying among ravines, boulders, tangled roots, and slopes too steep for wagons. A company might own thousands of acres filled with valuable timber, yet much of that wealth was trapped in place. A tree standing beyond the reach of a skid road had little commercial value. If horses could not pull it to water or rail, it might as well have remained standing. The industry had reached a mechanical bottleneck. Cutting technology had improved, sawmills had grown larger, and demand kept rising. But transportation inside the forest still depended on animal power. Logging did not need a better axe. It needed a source of force that could reach across the landscape, pull uphill or downhill, and move trees the mountains seemed determined to keep. Steam power had already transformed factories, ships, mines, and railroads before it entered the logging camp. Small auxiliary engines were commonly used to lift cargo, pump water, and turn winches. These compact machines were often called donkey engines because they performed the repetitive heavy labor once assigned to animals. In the 1880s, loggers on America's west coast began adapting the same idea to the forest. The basic concept was simple. Mount a steam boiler, engine, and winding drum on a wooden frame. Wrap steel cable around the drum. Run that cable through the trees to a fallen log. Then use steam pressure to turn the drum and pull the cable back toward the machine. Unlike a locomotive, the steam donkey did not need to travel under its own power. Horses, oxen, or another cable could drag it into position on wooden skids. Once anchored to a stump or standing tree, it became a stationary source of enormous pulling force. One of the earliest successful logging donkeys was developed in California by John Dolbear, a lumberman and inventor who patented a steam-powered logging engine in 1882. His machine allowed crews to haul logs from places animal teams could not work efficiently, especially on the steep and broken terrain of the redwood country. The first machines were crude. They leaked steam, consumed wood and water, and demanded attention. To anyone passing through the camp, they looked like iron boilers abandoned among the trees. But when the operator opened the throttle and the cable tightened, that awkward machine could pull several tons of timber toward it. The forest had gained a new kind of working animal, one made of iron, fire, steam, and wire. At the center of every steam donkey was a simple idea: turn heat into pulling force. A fireman fed wood into the firebox beneath the boiler. As the water heated, steam pressure built inside. When the operator opened the throttle, steam entered one or more cylinders and drove pistons back and forth. Connecting rods transferred that motion to a shaft, and the shaft turned a large winding drum wrapped with steel cable. The cable was the machine's real reach. Workers pulled it through the forest, sometimes hundreds of feet, and attached it to a fallen log with chains or metal hooks. When the drum turned, the cable wound back onto the machine, dragging the log toward the donkey. The operator could slow, stop, or reverse the drum, but every movement depended on signals from men he often could not see. The donkey itself had to be anchored securely. Crews chained it to a standing tree, buried deadman logs in the ground, or braced it against massive stumps. Without a strong anchor, the machine would pull itself across the forest floor instead of moving the timber. Pulleys, called blocks, made the system far more useful. By routing the cable around trees or through elevated supports, crews could change the direction of pull, guide logs around obstacles, and multiply force. They could sacrifice speed for power, allowing a relatively compact engine to move a load far heavier than its size suggested. Water and fuel were constant concerns. A donkey needed a steady supply of both, and remote crews sometimes built tanks or wooden flumes just to keep the boiler operating. The fireman watched the water level, the engineer watched the pressure gauge, and everyone watched the cable. Once the log started moving, crews kept the cable tight, because slack could snap violently when the drum suddenly took up the load again. A steam donkey did not push logs. It did not carry them. It stood still, gripped the earth through its anchors, and used steel wire to pull the forest toward itself. Before the steam donkey, a logging crew had to organize nearly every decision around the limits of animals. Roads had to be built where horses could climb. Trees were selected according to how easily their trunks could be dragged. If a log lay beyond a ravine, behind a ridge, or too far from a skid road, it was often left behind. The donkey changed that arrangement completely. Instead of moving the source of power to every log, crews placed the engine at a strategic point and extended its cable outward. The machine became the center of the operation. Lines ran through the forest like the spokes of a wheel, reaching logs hundreds of feet away and pulling them toward a landing where they could be loaded onto rail cars, sleds, or river transport. This new system also divided logging into specialized jobs. The fireman kept the boiler supplied with fuel and water. The engineer controlled the throttle and winding drums. Other men carried cable through brush, fastened chains around logs, cleared obstructions, and relayed signals back to the machine. Since the operator often could not see the load, the entire crew worked according to whistles and hand signals. Production no longer moved at the pace of a tired horse team. As soon as one log reached the landing, the cable could be sent back for another. Crews worked in a repeating cycle: pull out the line, attach the load, signal the engineer, haul the log in, and begin again. The effects spread beyond the logging camp. Sawmills received timber more steadily. Logging railroads could justify pushing farther into remote country. Trees once considered unreachable became profitable, and companies could harvest larger areas with fewer animals. The steam donkey did not merely make logging faster. It reorganized the forest into a mechanical system, with the engine at its center and every worker, cable, road, and tree arranged around its pulling power. The steam donkey multiplied human strength, but it did not remove people from danger. It placed them beside machinery operating under enormous tension. The men farthest from the engine often faced the greatest risk. Choker setters crawled through brush, climbed over fallen timber, and wrapped chains or wire chokers around logs. Line crews dragged heavy cable across steep ground, sometimes working where the engineer could not see them. Nearby, the fireman fed the boiler while the engineer watched pressure, controlled the drums, and waited for signals. Communication was critical. A logging site could be filled with the roar of steam, the clatter of gears, and the scrape of timber across rock. Shouted instructions were useless at long distances. Crews developed whistle codes, hand signals, and mechanical signal lines, so the engineer would know when to start, stop, slow down, or reverse. One misunderstood signal could be fatal. A steel cable under load stored tremendous energy. If it snapped, it could whip across the clearing faster than a man could react. A pulley could tear loose from its anchor. A log could swing sideways, roll downhill, or suddenly break free from a stump. Workers learned never to stand inside the bend of a cable or directly in the path of a moving load. Even experienced crews could be caught by changing tension, rotten anchors, or hidden obstacles. The donkey made impossible logging possible, but only because men worked close enough to its cables to guide every pull. The machine supplied the power, the crew supplied the judgment, and accepted the risk. As logging pushed into steeper country, the first single-drum donkeys reached their limits. Crews needed more distance, better control, and a way to move logs without dragging them through every stump, rock, and ravine. Manufacturers responded by adding more drums and more cable. One drum hauled the log toward the machine. Another pulled the main line back into the forest, so workers did not have to drag it by hand. With separate lines controlling the load, crews could work faster and recover cable across greater distances. Then, loggers began lifting part of the weight off the ground. They topped a tall standing tree and reinforced it with guy lines, turning it into a spar. Pulleys were mounted high above the forest floor, and cables ran from the donkey through the elevated rigging. When the engine pulled, the front end of a log rose into the air, while the rest skidded behind it. This high-lead system reduced friction, cleared obstacles, and allowed timber to be hauled across slopes that horses could never approach. Later Skyline systems suspended even more of the load, carrying logs over gullies, streams, and broken ground. The machines grew heavier, boilers became larger, drums multiplied, steel cables stretched farther across the mountains. A single setup could now reach timber scattered across a mountainside without relocating the engine. What began as a stationary winch had become an aerial transportation network built from steam, wire, and standing trees. At that point, the forest was no longer being logged only from the ground. It was being logged through the air. The steam donkey solved one of logging's greatest mechanical problems, but it also removed a limit that had protected many forests. Before cable logging, steep slopes, deep ravines, and unstable ground made some timber too difficult or too expensive to reach. Horses could only pull so far. Skid roads could only climb so high. Many trees survived simply because moving them was not worth the effort. Steam power changed that calculation. Once a donkey engine and its cables could reach across a mountainside, previously inaccessible timber became profitable. Crews could pull larger logs over longer distances and harvest slopes that animal teams had avoided. As machines grew stronger, companies cut more trees in less time and pushed farther into remote country. The damage did not end when the logs reached the landing. Heavy trunks dragged across the ground, tore through growth, disturbed soil, and carved channels down hillsides. Temporary roads, rail lines, camps, and cable corridors divided the forest. On steep terrain, loosened earth could wash into streams, covering spawning beds and changing the flow of water. At the time, these effects were rarely treated as part of the machine's cost. The important measurements were production, distance, and logs delivered to the mill. To logging companies, the steam donkey was an engineering triumph. It transformed difficult land into usable timber and made forests commercially accessible. But its greatest strength was also its most lasting consequence. It allowed the industry to cross natural barriers that had once slowed the saws down. By the early 20th century, the steam donkey had become one of the most important machines in American logging. But the same industry that had adopted it so quickly was already developing replacements. Steam power came with serious disadvantages. A donkey needed fuel, water, and time to build pressure before work could begin. Boilers demanded constant attention. Leaks, scale, damaged valves, and worn cylinders could stop production far from any repair shop. The machines were also extremely heavy. Moving one through a forest could require horses, temporary track, skids, or another cable system. Fire was another danger. Sparks from the stack and hot ash from the firebox could ignite dry slash left behind after logging. In summer, a machine built to harvest the forest could also help burn it. Then, internal combustion engines arrived. Gasoline and diesel yarders could start faster, operate with smaller crews, and eliminate the need for boilers. Crawler tractors and motor trucks made it easier to move logs directly overland. Better roads reduced the industry's dependence on fixed cable systems. The transition was gradual. Many steam donkeys continued working in remote camps for years, and some were converted to newer engines. But eventually their boilers went cold. Many were simply abandoned where they had last worked, because hauling them out cost more than the iron was worth. Today, the steam donkey has vanished from active logging, but it has not disappeared from the landscape. In old logging country across the Pacific Northwest, rusted boilers still sit among ferns and second-growth trees. Winding drums are frozen in place. Broken gears lie beneath moss. Lengths of steel cable vanish into the soil, and trees grow through frames that once shook under steam pressure. Some machines survive in museums and restored logging camps. Others remain exactly where crews abandoned them decades ago, too heavy and too remote to recover. These iron remains mark a transition between two worlds. Before the steam donkey, logging depended on animals, winter roads, and the limits of muscle. After it, forests became mechanical systems of engines, cables, signals, and specialized crews. The machine never traveled quickly. In many cases, it never moved while it worked. Yet from one fixed position, it could reach across a mountainside and pull giant trees out of terrain that had protected them for centuries. The steam donkey did not conquer the forest by moving through it. It conquered the forest by standing still and making the mountains come to the machine.